Hello, my name is Emmanuel De Leon, and I will be presenting a summary of vibration-based experimental damage detection of a small-scale wind turbine blade. For this presentation, I will provide an introduction, motivation, and goal of the study, discuss the two damage detection methods used with its results, and conclude with final remarks. Wind turbines have been used to extract and harness wind energy, accounting for almost half the global renewable energy sources. Wind turbines often operate in harsh environment sites, which set their nominal lifespan to 20 years. However, this is often not met, and in fact, only few turbines today have met their life expectancy. Among the structural parts, wind turbine blades are the most prone to damage and failure, as they are commonly made of composite materials. They suffer from hygrothermal effects, leading to further aging and deterioration. Within the context of structural health monitoring, a number of shortcomings have been reported relative to blade component damage detection. First, it is relatively difficult to extract response information from operating blade components due to complications in deploying sensors that can handle electromagnetic interference and rotation of the blades in the cell. Second, the flexible components have low natural frequencies, which increases the difficulty in detecting damage related to crack patterns. And third, it is difficult to appropriately simulate the blade components to understand the damage mechanisms involved. Existing structural health monitoring approaches rely largely on non-destructive evaluation techniques. Due to difficulties of on-site testing, blade components are typically tested in a lab environment. Although this is efficient, it needs to be validated in actual operation. Thus, the need for enhanced applicability of vibration-based damage detection tools are needed. The goal of the study was to apply, assess, and compare two widely used damage detection methods, in particular, the statistical and modal damage detection methods. The statistical method used in this study covered both non-parametric and parametric methods, while the modal method compared vibrational metrics of the operating and baseline healthy state conditions. For the experiment, the wind turbine blade was manufactured as a sandwich model. As seen in the figure below, there are 4 vertical shear webs of the blade to provide additional stiffness to avoid instability or buckling during operation. There were 4 directions of interest during this study, which are numbered on the figure as well. First, the leading edge pertains to where the airflow is in first contact. Second, the trailing edge is its rear edge. Third, the low pressure flap-wise side is the one that is upwind during operation, and opposite is fourth, the high pressure flap-wise. For the dynamic testing, the blade installation is shown in the figure on the slide. The blade was clamped at one end to a high stiffness horizontal steel beam. Also, rubber absorbers were placed between the blade and the beam to reduce noise during testing. A sensor grid of 8 accelerometers were installed on the blade based on a finite element method. 6 were mounted on the low pressure flap-wise surface, and 2 were placed on the leading edge of the blade. A point loading was applied at the high pressure flap-wise surface by an electromechanical shaker with pure white noise of an effective frequency band of 0 to 400 Hz for all testing cases. For the damage scenarios, artificial damage was placed in positions and types as shown in figure 3. The damage scenarios included masses that may accelerate fatigue accumulation and surface cuts at various locations to examine crack type flaws based on existing literature. Table 1 summarizes the damage type, description, and number of experiments completed for this investigation. For the non-parametric damage detection, 2 functions were used to measure the vibration response of the blade during operation. First, the power spectral density, or PSD function, was used to collect information on a particular blade position as shown in equation 2. The damage detection was based on statistically significant variations of the PSD function via hypothesis testing. With a selected risk level alpha, the null hypothesis H0 was accepted provided the ratio of the baseline and unknown states fell within the bounds of the F distribution curve as shown in equation 5. The amplitude of the frequency response function, or FRF, can be explored and is defined as shown in equation 6, where the cross-spectral density G is given by equation 7. The hypothesis testing was formulated as shown, where the null hypothesis was accepted if the difference between the FRF of the unknown and baseline states fell within the bounds of the standard normal distribution as shown in equation 8. For the parametric statistical damage detection, the basis of a model parameter vector theta was used as the characteristic statistical quantity. Damage detection was done by testing for statistically significant changes between the healthy and unknown structural states for the hypothesis testing shown. Following the chi-square distribution and a risk level, equation 11 shows that the null hypothesis was accepted provided the model parameter Q fell within the bounds of the chi-square distribution. For the representation of the structural dynamics, the following vector autoaggressive or VAR inputs in equation 12 were used in line with the parametric hypothesis test. Furthermore, vector autoaggressive with exogenous or VAR-X inputs were implemented into statistical damage detection as shown in equation 16. Without going through the rigorous math, the model parameter theta can be extracted from equations 12 and 16. For modal damage detection, the most important vibration modes as shown in the slide were tracked. These parameters were estimated during the baseline and inspection states using a VAR or VAR-X model. For the baseline phase, the first dataset samples were acquired for the healthy structural identification of the blade. In figure 4, it is shown that there is a strong contribution of the applied white noise input to the vibration acceleration outputs in the 10 to 400 Hz band. For figure 5, the estimated sample FRFs indicate 6 structural frequencies that were used for analysis in the inspection phase, where the edgewise direction modes appear larger than those of the flapwise direction. For the statistical damage detection in the inspection phase, the remaining datasets were considered to correspond to an unknown state of the blade utilizing the decision-making process discussed previously. For figures 6 and 7, positions 2 and 6 were selected due to their placement between cracks and most distant to damages flapwise, respectively. The baseline healthy structure plots are provided on top of each figure where the blade was healthy below the red threshold line. With a significance level of 99%, Figure 6 shows that the PSD-based method exhibited diverse performance with respect to the sensor position. However, false alarm results were more frequent for position 2 as shown with test points still below the red threshold line. For position 6, the method returned failed decisions for most of the damage types and completely failed for type A. In contrast to figure 7 for the FRF-based estimates, very few missed faults were detected, namely for damage types H and I. For figure 8, parametric estimates reveal that they are able to detect all damage cases accurately with no missed faults in both the VAR and VAR-X settings. For the modal damage detection results, figures 9 and 10 showed that the high sensitivity of the vibration modes to a given damage type highly varies and that no single mode, frequency, or damping ratio may serve for detecting all damage types. For mode 1, the VAR models successfully detected damage in both frequencies and damping ratios, with the exception of type A. In modes 2 and 3, the VAR models better predicted damage types with the damping ratios. In modes 4 to 6, no clear indications were provided from either frequency or damping ratios. For the VAR-X models, no clear indications were provided overall, as no clear patterns in either the natural frequency nor damping ratios were observed and yielded inconsistent results, thus could not provide any clear decision-making authority in damage detection. The next 2 slides further assess the vibration modes as damage-sensitive features and serve to support the results of the previous slide. In the figure shown, damages C and L were provided to be the most severe cases. The VAR mode shapes and mode shape curvatures proved quite sensitive to damage C as reflected in modes 4 through 6 shapes in figure 11 and all the curvatures in figure 13. The same damage types in the VAR-X models show similar patterns. The influence of the actual inflicted damage is clearer for the higher modes. In conclusion, The PSD is able to detect damage in certain cases, although inaccurate, being highly dependent on the location of the sensors, whereas the FRF proves to be more convenient as no false alarms were produced and behaved more consistently. For the parametric statistical damage detection, both input-output and output-only modeling are robust as no false alarms were activated and were more consistent. As observed, the integration of input information does not necessarily lead to more accurate damage detection for both statistical and damage modal techniques. However, the VAR models prove to be more accurate than VAR-X models in several cases. Finally, modal damage detection is effective only for certain vibration modes. Also, systematic decision-making cannot be carried out as the same damage may not be consistent with different modal parameters. Overall, statistical damage detection methods can be integrated into maintenance processes, as this experiment showed that statistical-based methods tend to outperform modal-based methods in detection of induced damage. However, a number of critical issues still need to be investigated and must be addressed for effective structural health monitoring for wind turbine blades over their life cycles. That concludes my presentation. Here are my resources, and thank you for listening.